Hi, welcome back to Chemical Kinetics class 4. Okay, in this we'll discuss about collision theory remaining parts. We were discussing class 3. You can continue. I just wanted to give you a break. Okay, now water break like that. Okay, so come back to this. This is exothermic graph and this is endothermic graph. Okay, here we are taking energy. You can say potential energy. Energy is taken here. This is of reactants and this is of products. Reactants, products. As we were discussing in the last class, it is threshold energy. Okay, now threshold energy. T I am writing threshold energy, and this is energy of activation, and this is again energy of activation. Backward reaction. If we are discussing about forward and backward reaction, here you can see for exothermic reaction, forward activation energy is less than backward. Okay, that lines are mentioned here. You can see heat of reaction delta E is equals to forward and backward. See, this is delta H. So delta H plus activation energy of forward is equals to activation energy of backward, where EAF is the energy of activation of the forward reaction and EAB is the energy of the backward reaction. Okay, now activation energy of the backward reaction. See, here for exothermic reactions, activation energy of forward reaction plus delta H is equal to energy of backward reaction. Same thing you can notice here. This is delta H. These are the products and these are the reactants. So this is activation energy of forward reaction and this is activation energy of backward reaction. So in this endothermic changes, you can say energy of forward reaction, activation energy of forward reaction is equals to activation energy of backward reaction plus delta H. Okay, now graphs questions only will be asked, and just to draw the graph and get this. For example, they will ask you activation energy is 15, delta H is equals to plus 10. Okay, now what is the meaning of delta H is equal to plus 10? This is endothermic change. Okay, now activation energy is 15, delta H is endothermic, means you need to put the graph like this, and delta H, this is 10 they mentioned, this is 15. So how much of this is? Directly you can say it is 5, because 15 is equals to 10 plus 5. So use this common sense and answer these questions. Okay, now chemical kinetics, class 12, class 4, we are discussing collision theory. Here with Lucky sir, right? It is in an exothermic reaction, the energy of the activation of the forward backward reaction is greater than the energy of the activation of the forward reaction. This is exothermic. You can see about this graphs I mentioned, and this is the same thing we are explaining here. Okay, this is the graph. Okay, energy of activation of the backward reaction is greater than the energy of activation of this. You see, this is backward is greater than the forward. In an endothermic reaction, the energy of the activation of the backward reaction is less than the energy of activation. That's what I was telling you. This is energy of the backward reaction, this is energy of the forward reaction. In exothermic reaction, backward activation energy is more. In endothermic reaction, forward activation energy is more. That lines are mentioned here. A plus B gives rise to products. Rate of reaction can be expressed as rate is equals to ZAB and e to the power of minus EA by RT. This is one type of expression, you can say Arrhenius expression type of expression, and this can be explained like this. You can see here these lines. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency. Collision frequency is given by Z. This is Z, where ZAB represents the collision frequency of reactants A and B, and e to the power of minus EA by RT represents the fraction of molecules with the energy is equal to or greater than the activation energy. This is the fraction of molecules with or equal to activation energy. This is the collision factor, and you are discussing about rate. So the proper orientation of reactant molecules lead to the bond formation, where the improper orientation makes them simply bounce back and no products are formed. This is only called fruitful collisions. Okay, now for example, it is coming like this. It is coming like this. Is, you say, fruitful collisions. For example, if they are coming like this, it is not a fruitful collision. Okay, this is fruitful and this is not a fruitful collision. So that must be in a proper orientation also. To account for effective collisions, another factor rho is called possibility or steric factor is introduced. It takes into account the fact of the collision. Molecules must be properly oriented. Okay, now not only collisions, proper orientation is also mandatory. That term is given by rho into z. Then coming to these points, the relationship between the rate constant of a reaction and temperature is given by K is equals to AE to the power of minus EA by RT. This is called Arrhenius equation. Or K is equal to rho into, this is rho actually, rho into Z into EA to the power of minus EA by RT. Okay, now rho into Z into E to the power of minus EA by RT. This rho into Z, in terms of this, we are keeping as A. A is called Arrhenius factor. A is the frequency factor. It gives the number of collisions per second per unit volume of reactants mixture. A is Arrhenius factor or frequency factor. It gives the number of collisions per second per unit volume of reactant mixture. You need to remember this expression, that's all. K is equals to A E to the power of minus EA by RT. Just remember this one, where A is rho and Z combination. That is product of rho and Z. The frequency factor A and energy of activation EA and are constant for a given reaction. They vary very slightly with temperature, so that they are almost independent of temperature for a given reaction. Practical fact it is, on taking logarithms on both sides of Arrhenius equation, you can get this equation. ln k is equals to ln A minus EA by RT, or log k is equals to log A minus EA by 2.303 RT. Okay, now in place of ln, if you are taking log k, it will become, okay, this is ln 2.303. You need to multiply. When a graph is drawn between log k and 1 by t, the graph will be like this. Okay, now log k and 1 by t graph will be like this, where slope is minus EA by 2.303 R. Minus EA by, this is negative slope, and negative slope is minus EA by 2.303 R. Fine. You need to remember this point also. Then coming to, before going to class 5, we will complete this part. Arrhenius equation, when you are taking for two different temperatures, you will be getting this expression, log K2 by K1 is equal to EA by 2.303 R, T2 minus T1 by T1 T2. Or you can say like this, log K2 by K1 is equal to EA by 2.303 R 1 by T1 minus 1 by T2, or simply T2 minus T1 by T1 T2. Okay, this is the most important equation in this lesson you are going to use for all your numericals. What happens? They will be asking you generally activation energy by giving K1, K2 values at two different temperatures. Like that, they will say at 200 Kelvin K1 is 1, at 300 Kelvin K2 is 4. What is the activation energy? Like that, they will give you. Okay, so R value, if you are using 8.314 joule, activation energy you are getting in joules. If you are using 8.314 into 10 to the power of 7 egg, you will be getting activation energy in X. If you are using R value as 2 calories, you will be getting joule per mole per Kelvin, of course. Okay, now per mole per Kelvin. So the units of R decide the units of activation energy. Okay. So K1, K2, these are the specific reaction rates, or you say rate constants at different temperatures. EA is activation energy, R is gas constant. Okay, now by using this, you can calculate the activation energies, you can calculate the different temperatures, you can calculate K1 or K2 or K2 by K1 ratio also. Done. We'll meet in class 5 with rate law.